The magnetic field of a current-carrying conductor. Introduction. Electricity and magnetism are two of the most fascinating forces in nature. They are deeply interconnected, and one of the most intriguing examples of this relationship is the magnetic field produced by an electric current. When an electric current flows through a conductor, it creates a magnetic field around it. This phenomenon is not only fundamental to our understanding of physics but also forms the basis for many modern technologies, from electric motors to MRI machines. Today, we'll explore how a current-carrying conductor generates a magnetic field, the shape and behavior of this field, and its significance in science and technology. Chapter 1. The Basics of Magnetic Fields. Before diving into the specifics of a current-carrying conductor, let's start with the basics of magnetic fields. A magnetic field is a region in space where a magnetic force can be detected. We often visualize magnetic fields using lines of force, which show the direction and strength of the field. The closer these lines are to each other, the stronger the magnetic field. Magnetic fields are produced by moving electric charges. This means that whenever an electric current flows, whether through a wire, a coil, or any other conductor, it generates a magnetic field around it. The relationship between electricity and magnetism was first discovered by scientists like Hans Christian Ørsted and later formalized by James Clerk Maxwell in his famous equations. Chapter 2. A current-carrying loop and its magnetic field. Let's focus on a specific example, a circular loop of wire carrying an electric current. Imagine a simple loop of wire, like a ring, with an electric current flowing through it. From a side view, the loop appears as a straight line, but in reality, it's a circle. When current flows through this loop, it creates a magnetic field around it. The magnetic field lines form loops that pass through the center of the ring and curve around the outside. Inside the loop, the field lines point in one direction, let's say upward, while outside the loop, they point in the opposite direction, downward. This creates a cylindrical symmetry around the axis of the loop, meaning the field looks the same no matter how you rotate the loop around its central axis. Chapter 3. Visualizing the magnetic field. To better understand the magnetic field, let's visualize it. Imagine the current-carrying loop lying flat on a table. If you could see the magnetic field, it would look like a series of blue loops surrounding the wire. These loops are denser near the wire, indicating a stronger magnetic field, and spread out as you move away, showing that the field weakens with distance. For simplicity, we'll focus on the magnetic field in the vertical plane that cuts the loop in half. In this plane, the field lines are easiest to visualize. They form smooth curves that pass through the center of the loop and extend outward. The density of these lines gives us an idea of the field's strength. The closer the lines, the stronger the field. Chapter 4. The right-hand rule. One of the most useful tools for understanding the direction of a magnetic field is the right-hand rule. This rule helps us determine the direction of the magnetic field based on the direction of the current. Here's how it works. 1. Point your right thumb in the direction of the electric current flowing through the loop. 2. Curl your fingers around the loop. The direction your fingers curl represents the direction of the magnetic field lines. Using this rule, we can see that a counterclockwise current produces magnetic field lines that point upward inside the loop and downward outside the loop. This simple rule is incredibly helpful for visualizing and predicting the behavior of magnetic fields in various situations. Chapter 5. The magnetic field at a distance. As we move farther away from the current-carrying loop, the magnetic field changes. At distances much greater than the radius of the loop, the field starts to resemble that of a magnetic dipole. A magnetic dipole is essentially a pair of magnetic north and south poles separated by a small distance. In this case, the loop behaves like a tiny bar magnet. The strength of this dipole field decreases with distance, following an inverse cube law. This means that if you double the distance from the loop, the magnetic field becomes 8 times weaker. This behavior is similar to how the gravitational force weakens with distance, but in this case, it's the magnetic field that's diminishing. Chapter 6. The concept of vector potential. To describe the magnetic field mathematically, scientists use a concept called the vector potential. While this might sound complicated, think of it as a tool that helps us calculate the magnetic field more easily. The vector potential is related to the magnetic field in a way that simplifies many calculations, especially when dealing with complex shapes like loops or coils. For a current-carrying loop, the vector potential can be calculated using special functions called elliptic integrals. These integrals provide an exact solution, but they can be quite complex. Fortunately, For most practical purposes, we can use simpler approximations that are almost indistinguishable from the exact solution. These approximations make it easier to visualize and understand the magnetic field without getting bogged down in complicated math. Chapter 7. Magnetic Induction and Scalar Potential. The magnetic field is also related to another concept called magnetic induction, often denoted by the letter B. Magnetic induction is a measure of the strength and direction of the magnetic field at any point in space. It can be calculated using the vector potential, but there's another way to represent it, using a scalar potential. A scalar potential is a simpler way to describe the magnetic field, especially in situations where the field is static, not changing over time. The scalar potential is related to the magnetic field in a way that allows us to calculate the field by taking the gradient, a kind of slope, of the potential. This approach is particularly useful for solving problems in magnetostatics, where the magnetic field doesn't change with time. Chapter 8. Magnetic Lines of Force and Equipotential Contours. To visualize the magnetic field, we often use two types of lines: magnetic lines of force and equipotential contours. Magnetic lines of force show the direction of the magnetic field at every point, while equipotential contours represent regions where the scalar potential is constant. These two sets of lines are always perpendicular to each other. This means that if you draw the magnetic lines of force, the equipotential contours will cross them at right angles. This relationship helps us understand the structure of the magnetic field and how it varies in space. Chapter 9. Applications of magnetic fields. The magnetic fields produced by current-carrying conductors have countless applications in science and technology. Here are a few examples. 1. Electric motors. Electric motors rely on the interaction between magnetic fields and electric currents to generate motion. A current-carrying coil in a magnetic field experiences a force, causing it to rotate. This principle is used in everything from household appliances to industrial machinery. 2. Generators. Generators work on the opposite principle of electric motors. They convert mechanical energy into electrical energy by moving a conductor through a magnetic field, inducing an electric current. 3. Magnetic resonance imaging, MRI. MRI machines use powerful magnetic fields to create detailed images of the inside of the human body. The magnetic fields align the spins of hydrogen atoms in the body, and radio waves are used to produce signals that form the images. 4. Transformers. Transformers use magnetic fields to transfer electrical energy between circuits. They are essential for stepping up or stepping down voltages in power distribution systems. Chapter 10. The magnetic field of a point dipole. As the size of the current-carrying loop becomes very small, its magnetic field starts to resemble that of a point dipole. A point dipole is an idealized concept where the magnetic field is produced by two infinitely close magnetic poles. This simplification is useful for understanding the behavior of magnetic fields at large distances. The field of a point dipole decreases rapidly with distance, following the inverse cube law. This means that even though the field is strong near the dipole, it becomes very weak as you move away. This behavior is similar to how the gravitational field of a small object weakens with distance. Chapter 11. The Role of Symmetry. One of the most striking features of the magnetic field produced by a current-carrying loop is its symmetry. The field is cylindrically symmetric, meaning it looks the same no matter how you rotate the loop around its central axis. This symmetry simplifies many calculations and makes it easier to predict the behavior of the field. Symmetry is a powerful tool in physics. It allows us to make predictions and solve problems without having to consider every detail. In the case of a current-carrying loop, the cylindrical symmetry of the magnetic field is a direct result of the circular shape of the loop and the uniform distribution of the current. Chapter 12. Magnetic Fields in Nature. Magnetic fields aren't just a human invention, they are a fundamental part of nature. The Earth itself has a magnetic field, which protects us from harmful solar radiation. This field is generated by the motion of molten iron in the Earth's core, creating a dynamo effect. Many animals, such as birds and sea turtles, use the Earth's magnetic field for navigation. They have specialized cells that can detect the field, allowing them to find their way over long distances. This natural ability is a testament to the importance of magnetic fields in the world around us. Chapter 13. The Future of Magnetic Field Research. The study of magnetic fields is an active area of research with many exciting possibilities. Scientists are exploring new materials that can generate stronger magnetic fields, as well as new ways to manipulate magnetic fields for advanced technologies. One promising area is spintronics, where the spin of electrons is used to store and process information. This could lead to faster and more energy-efficient computers. Another area is magnetic levitation, where magnetic fields are used to lift and propel objects, potentially revolutionizing transportation. Conclusion. The magnetic field produced by a current-carrying conductor is a beautiful example of the interplay between electricity and magnetism. From the simple loop of wire to the complex fields used in modern technology, this phenomenon has transformed our world. As we continue to explore the mysteries of magnetism, we can look forward to new discoveries and innovations that will shape the future.